Today, my name is Johnny Tew, and I am the corresponding author for this paper, Wave Analysis of a L-beam Structure with a Blocking Mass. Wave analysis, or the wave propagation method, is an alternative means of analyzing the vibration response of a structure. The basis for wave analysis involves the representation of vibration present within any structure as waves flowing along structural members such as beams or plates. And upon meeting various discontinuities, these waves are split into reflected and or transmitted components. Now, each specific discontinuity can be represented in matrix form based on the fundamental equations describing vibration and applying a specific boundary condition that accurately represents said discontinuity. Since each discontinuity has a specific matrix associated with it, one can use a combination of matrices of varying types to represent or model a structure. This in turn becomes increasingly useful for structures with repetitive elements and types of discontinuities such as planar frames. So in order to properly model the response of the L-beam structure, first the transformation matrices must be determined using the fundamental equations. These include the boundary matrices, such as free, fixed, or simply supported edges, reflection and transmission across the joint, which I'll go into later, and the propagation of the waves along the beam elements. For wave analysis, you must also obtain the wave relations. These are equations showing the relationship between various wave components of the structure. These wave relations can then be combined to make a global matrix, which can then be used to obtain the response of the structure, in this case, the natural frequencies. And finally, I will be manipulating the blocking mass parameters to see how it affects the response of the structure. The overall methodology used in the study is heavily based off of May and Mace's work shown in the references. Below are the equations of motion for the in-plane vibration of a Timoshenko beam. The fundamental equations are manipulated in various ways to obtain the transformation matrices, which are outlined in the paper. But I would like to highlight two specific matrices used in the L-beam structure, f of x, which is the propagation matrix, and RC, which is the boundary condition for a clamped edge. On the left is the overall L-beam structure, which is in essence two beams, beam 1 and 2, connected at a right angle, resulting in joint J. Now at the ends of each beam, there exist two wave components, a positive and negative leading one. For example, A minus and A positive. These are denoted by the arrows. Now to obtain the wave equations and wave relations, one simply needs to observe which wave components are flowing into each other and how they are affected. They are split up into three domains. Boundary reflection, so that would be at this point here and here. Joint reflection and transmission, which would be the outward coming components of the joint, which would be J2 minus and J1 plus, and the propagation of the waves along the beam. So that would be A plus, B minus, and J2 plus, and J1 minus. The wave relations on the previous slide can then be combined to form a wave coefficient matrix, A, and a wave component matrix, C. It is important to note that what is shown here is a simplified representation of the true global matrix. When in actuality, each element in this 8x8 matrix here is actually a 3x3 matrix, so the overall global matrix would be a 24x24. Now by calculating the determinant of A, the coefficient matrix, one can obtain the characteristic polynomial of the structure. This characteristic polynomial can then be graphed in terms of its frequency to obtain the plot shown. At each point where the graph touches the x-axis, it results in a natural frequency. Using a self-written MATLAB code, the graph was imported, and the cross points or natural frequencies were calculated by finding the local minima of the graph. This results in the table you see on the right, which are the natural frequencies of the system. The previous model for the L-beam structure was then manipulated to include a scaling factor alpha for the size of the joint, as well as the ability to manipulate the material of the joint, after which the existing transformation matrices for the joint were updated. The same procedure of using the wave coefficient matrix and subsequently the characteristic polynomial was then used to obtain the natural frequencies for the new L-beam structure with the blocking mass, using various scaling factors. As you can see, the discrepancy between the two models of the ANSYS and the wave model began to increase as the mode number for the frequency increased, as well as the scaling factor increased. The 3D surface plots you see here are the individual components of the joint transmission matrix, shown in blue, and the joint reflection matrix, shown in orange. When examining the components of the matrices, it was noted that there existed a transition band across the bending waves. The initial transition frequency is increased to the scaling factor, and that is the size of the joint, and shows that the transmission of the bending vibration becomes much larger than reflected after a certain frequency. This, however, is superseded by a secondary transmission frequency, which is also affected by the scaling factor alpha, whereby the magnitude of the transmitted bending vibration degrades to zero, leaving only the reflected component. This is described as the total reflection effect by Kreml, Haeckel, and Peterson, which is a property of blocking masses. By manipulating the joint material, the mass of the joint would also change. This results in a variation in the natural frequencies across the different materials. It can be seen that the wave model holds up fairly well to the ANSYS model across all materials. However, the accuracy of the model begins to degrade as the mode number increases. This could be attributed to the exclusion of the actual flexibility of the joint, as the joint was modeled as a rigid structure. As it stands, the wave model is currently limited to fairly simple planar structures due to just considering the in-plane motion. However, this can be expanded by also considering the out-of-plane motion at the same time. This is also constrained by the number of members and the types of discontinuities in terms of calculation, but this is currently being worked on. And as it stands, the wave model only holds up for low scaling factors due to, as the joint increases, it becomes dominant in the structure and the flexibility becomes much more important. And as I said before, the out-of-plane motion must be included. These are some of the papers I've referenced during the presentation: May, Mace, and Kramer, Haeckel, and Peterson. That is the end of my presentation. If you have any more further technical questions, you can forward them to my email shown below.